So you just finished taking your test 2 part 1, and I want you to grade your exam. And so the first question says, use the graphs shown below to find the limit as x approaches 2 of f of x divided by g of x. If you look at this and we look at the limit as x approaches 2 of f of x, we can see as x is getting closer and closer to 2, we're approaching the value of 0. This is the same thing as using rules of limits. The limit as x approaches 2 of this rational expression is the same thing as the limit as f of x approaches 2 of f of x all over the limit as x approaches 2 of g of x. If we look at what's happening as we're approaching 2 on g of x, again, we're getting closer and closer to 0. So we get 0 divided by 0, which is an indeterminate form. Since it's an indeterminate form, we can use L'Hopital's rule. And so L'Hopital's rule says that this limit will be equivalent to the limit as x is approaching 2 of f prime of x all over g prime of x. We're given here, so this would be the same thing as f prime of 2 all over g prime of 2. On this graph, we're given the equation of the tangent line. And so if we are looking at the equation of the tangent line, or the tangent line here, we can figure out what the slope is. And so here, if I'm looking at it to points that I see on here, I'm going to rise 2, and then I'm going to run over 4. So this is 2/4 all divided by g prime of 2. So again, if I look at the equation of the tangent line, or the graph of the tangent line, I see I have a point here. Looks like I have a point here. So I'm rising up 4 and running over 1 to the right. So let's just simplify this. We have 1/2 divided by 4, which is the same thing as multiplying by the reciprocal 1/4. And so the limit as x approaches 2 of f of x divided by g of x is going to give us 1/8. So this problem was worth 5 points. Give yourself 5 points if you got this correct. You showed your work, explained what you were doing, and then start deducting points for errors or not knowing what you were doing. So question 2 says, look at the limit as x approaches 0 of sine of x minus x. That quantity is all over cosine of 2x minus 1. So first thing you want to do when you're doing limits is do direct substitution. And so if we go in here and we plug in 0 wherever we see an x, we get the following. This is equal to sine of 0 minus 0 all over cosine of 2 times 0 minus 1. Well, sine of 0 is 0, and so 0 minus 0 gives us 0 in the numerator, all over cosine of 0, which is 1, and 1 minus 1 gives us 0 in the denominator. And so again, we have an indeterminate form, and so we can use L'Hopital's rule. And so looking at the limit as x approaches 0 of the derivative of the numerator, so the derivative of sine of x is cosine of x, minus the derivative of x, which is 1, all over the derivative of cosine of 2x. So we need to use the chain rule there. The derivative of the outer cosine is negative sine of the inner 2x times the derivative of the inner function 2x. Derivative of 2x gives us times 2. Minus the derivative of a constant 1, which is 0. So now again, we want to go through and we want to do direct substitution, plugging in 0 wherever we see an x. And so doing that, we get cosine of 0 minus 1 all over 2, or negative 2, times sine of 2 times 0. Cosine of 0 again is 1. 1 minus 1 in our numerator gives us 0. Sine of 2 times 0 is sine of 0 is 0. So we get 0 over 0 indeterminate form. And so we're going to apply L'Hopital's rule a second time. So looking at the derivative of cosine of x, bring down the limit as x goes to 0. Derivative of cosine of x again is negative sine of x. Derivative of this 1 is 0, all over the derivative of negative 2 times the derivative of sine of 2x. So using the chain rule, we have the derivative of sine is cosine of the inside, 2x, times the derivative of the inside, which is 2. Go in and do a direct substitution, and so we get this is equal to negative sine of 0 all over negative 2 times 2, so negative 4 cosine of 2 times 0, which is 0. And so this gives us 0 over negative 4, which gives us 0. So for number 2, part A, you should have gotten 0. That's worth 5 points. So going over to part B, we have the limit as x is approaching 1 of 2 times the natural log of x all over 1 minus e to the x minus 1 power. So again, we're going to go in and we're going to do direct substitution. And so we have 2 natural log of 1 all over 1 minus e raised to the 1 minus 1 power. So this gives us 2 times the natural log of 1. Well, natural log of 1 is 0. 2 times 0 gives us 0 all over 1 minus e to the 0. Well, e to the 0 is 1, so we have 0 over 1 minus 1, which is 0. And again, we have an indeterminate form. And so we're going to go through and we're going to use L'Hopital's rule again. So we're going to look at the limit as x is approaching 1 of the derivative of our numerator, 2 times the natural log of x. That's going to be 2 over x, all over the derivative of 1, which is 0, minus the derivative of e to the x minus 1. Well, the derivative of e to the x minus 1 power is just itself, e to the x minus 1, times the derivative of the exponent, and the derivative of x minus 1 is just 1. So now if we do direct substitution and we plug in 1, we get 2 all over 1 divided by negative e to the 1 minus 1 power. So this gives us 2 all over negative e to the 0 power is negative 1. And so you should have gotten negative 2 as your answer. So that part is also worth 5 points. Number 2 is worth 10 points altogether. So number 3, you have h of x is equal to a times the quantity 1 minus e raised to the negative bx power, where a and b are both positive real numbers. So part A, you want to find the intervals where h of x is increasing and decreasing. So we want to find our critical values, and that's where our derivative is equal to 0 and undefined. And so we want to find h prime of x. Before we do that, just so I don't have to use a product rule, which I guess it's not a huge deal, let's distribute that constant a. So a times 1 is a minus a e to the negative bx. Okay, so now let's take the derivative of this. So the derivative of h of x is equal to the derivative of a, well, that's a constant, so that's 0, minus a times the derivative of e to the negative bx. So the derivative of e is itself, e to the negative bx. We need to use the chain rule, and so times the derivative of the exponent, which is negative b. So I get that h prime of x is equal to negative ab e to the negative bx. So I want to find where this is equal to 0 and where it's undefined. Well, it's defined everywhere, and then looking at when is negative ab times e to the negative bx equal to 0. Well, e to the negative bx, there's no value that will make x equal to 0. This is not possible. So this tells me that this is either strictly increasing or strictly decreasing. And this is defined everywhere, the derivative. And so let's just try one value. If we plug in 0, we want to, into the derivative, we want to see is this positive or negative. So just plugging in any value for x. So we get negative a times b e to the negative b times 0. This is equal to negative ab. Well, e to the 0 is 1. We know a and b are both positive, so this times the negative in front we know is less than 0. So this is strictly decreasing. Actually, I made a mistake up here. I thought something was off. The derivative of negative bx. Derivative of negative bx is negative b. So it should have been a negative b, which makes that a positive ab e to the negative b times 0. And this is always greater than 0. And this is strictly increasing, not decreasing. So part B wanted you to find the intervals of concavity. Where was it concave up, concave down? And so now we need to look at the second derivative. And so looking at the first derivative, we had this was equal to, did something go wrong? H prime of x, this should have been negative b, this is now positive, this is now positive. There we go. So we're now looking at ab e to the negative bx, looking at the derivative of that. So the second derivative, we have ab all times the derivative of the exponent, which is negative b, times e itself, e to the negative bx. So this is equal to negative ab squared, e to the negative bx. So if we plug in a value in here, so maybe 0 again, this would give us negative ab squared, e to the 0. E to the 0 is 1. And so this is going to give me a number that is less than 0. So I know that it's concave down everywhere. This value, h double prime of x, when we were looking for a critical number or inflection point, again, same reasoning as above. There's no way that this could ever equal 0. There's no value of x which would set this equal to 0. And then the last piece was looking at the end behaviors of your graph of h of x. And so if we look at the limit as x is approaching negative infinity of this a minus a e raised to the negative bx, and we plug in negative infinity wherever we see an x, this is going to give us a minus a e raised to the negative b times negative infinity. Well, if I'm taking a minus a and I'm taking b and raising it to e and raising it to a positive number that's going off to infinity because a negative and a negative. This is going to be shooting off to infinity and a constant minus infinity. So this end behavior, this is shooting downwards. It's going to negative infinity. Now looking at the limit as x is approaching positive infinity of a minus a e to the negative bx. When we plug in positive numbers, a minus a e to the negative b times positive infinity, let's use rules of exponents. We can bring that negative exponent, e, down to the denominator. So this is a minus a all over e to the b times infinity. Well, this portion over here, this fraction is going to 0. And so we're left with a minus 0, which is a. So we actually have a horizontal asymptote at y equals a as h of x goes off to positive infinity. Okay, so that was number 3. Each piece is worth 5 points, total of 15 points. So number 4, you're given information about the graph of f of x, and you want to graph the function. And so we're given that the function passes through the points negative 2, 2. So we might as well just plot those. So negative 2, 2, negative 1, 1, 0, 0, 1, 1, and 2, 2. And then we're given that the function is twice differentiable and has the following signs when plugged into the first and second derivative. So basically we're given a sign chart here. And so if right here, f prime of negative 2 is either equal to 0 or undefined, but we're given it's twice differentiable. So we have something that is increasing until we get to negative 2 and then decreasing until we get to 0. Let's look over here. On the left of negative 1, so this is my double derivative, it's negative. And so I'm going to see that negative 1 is an inflection point. If it's negative, then I know that it's concave down here. And this was increasing. So increasing, concave down. Could look like this. Concave down until I get to 1. And now it's starting to be concave up. It's decreasing until I hit 0, and then it's increasing until I hit 2. And I know that here it's concave up between negative 1 and 1. So this right here is another inflection point, and now it's going to start to be concave down again after 1. When I hit 2, x equals 2, I then see that I'm starting to decrease again. And so I'm going to come down, and it's going to be concave downwards for the rest. So you should have some sort of graph that looks similar to this. That one is worth 5 points. So the last problem, number 5, for f of x equals the square root of x minus 1 on the interval from 1 to 3, find c such that f prime of c is equal to f of b minus f of a all over the quantity b minus a on that interval. So there's a couple things that we need to do. We need to figure out what f of 3 is. So if we go in and we plug in 3, wherever we see an x, we have the square root of 3 minus 1, which is the square root of 2. So I know I have a point at 3 root 2. And then let's plug in 1. So plugging in 1, wherever we see an x in the original function, we have the square root of 1 minus 1, which is the square root of 0, which is 0. So we also have a point at 1, 0. So now let's look at f of b minus f of a. And actually, yeah, so f of b minus f of a, that's f of 3 minus f of 1 all over 3 minus 1. So in our case, we have root 2 minus 0 all over 3 minus 1, which is 2, which is root 2 over 2. So let's find the derivative of f of x. Before we do that, let's rewrite it a little bit. So f of x could be rewritten as x minus 1 all raised to the 1/2 power. So let's use the chain rule when we're taking the derivative of this, bringing our power down front of the inside x minus 1, subtract 1 from our power, so 1/2 minus 2/2 is negative 1/2, times the derivative of the inside, which is 1. So we're looking at when is, and I'm going to rewrite this a little bit, 1 over 2. So x minus 1 to the negative 1/2, I'm going to bring it down to the denominator and rewrite it as the radical. So when is 1 over 2 square root of x minus 1. We're looking at when is this equal to root 2 over 2. So we want to solve for x here, and that will be our value of c, which makes this true. And so let's clear a fraction, or at least one of them. Let's multiply both sides by 2 square root of x minus 1 on both sides of our equation. So that cancels, leaving us with 1 on the left equals, my 2 cancels here, root 2, all times the square root of x minus 1. So let's square both sides of our equation. So we get 1 is equal to 2 times the quantity x minus 1. So I get 1 is equal to, distributing our 2, we get 2x minus 2. Add 2 to both sides. We get 3 is equal to 2x. Divide both sides by 2. We get x is equal to 3/2. I just need to make sure that that is a true statement because I squared both sides of my equation here. And so it's possible to get solutions which are extraneous. And so I need to make sure that it's not an extraneous solution. The other thing that you need to make sure is that it's falling within the interval that we're looking at. And 3/2 does fall within the interval of 1 and 3. So let's just check. So if I plugged it in to this, where did it go? Is that a true statement? So is 1 all over 2 square root of 3/2 minus 1, is that truly equal to root 2 over 2? Okay, so we have 1 all over 2. I'm going to get a common denominator. So this would be the square root of 3/2 minus 2/2, which is 1/2. Is this equal to root 2 over 2? So let's do a little bit of manipulating. So we have 1 all over 2 square root of 1, which is 1, all over root 2. So this is equal to 1 all over 2 root 2, which if we invert multiply, we got root 2 all over 2. Is that equal to root 2 over 2? Yes. Okay, so we found the value of c, which makes this a true statement. And so c is going to equal 3/2. So that one also is worth 5 points. So now take your time, sum up the points that you got for each problem, and then put your score on the top of the page of your test and submit that to Canvas.